Hello and welcome to the presentation of our paper, Privately Connecting Mobility to Infectious Diseases via Applied Cryptography. This paper is a joint work with Alexandros Bambolidis, Alessandro Bruni, Lukas Helminger, Daniel Kales, Christian Rechberger, and me, Roman Walch. When we have a look at the recent COVID-19 pandemic, we can see that a lot of technical solutions have been proposed to help the population with contact tracing. So people could decide to install an app, activate Bluetooth, and when they have been in contact with another app user who has later been tested positive with the virus, and they get a notification from the app that they might be positive as well. However, the success of this app crucially relies on a large chunk of the population actually installing and using this app. So when we wanted to help containing the spread of the disease, we thought of a different solution which does not rely on an app. So what we wanted to do is, we wanted to create a heat map which aggregates the location data of infected individuals. And this heat map is intended to keep track of the spread of the disease and help policymakers in making some measures which help containing the disease. And for example, they can take some targeted measures for closing off public places which are located inside of some hotspots. And crucially, our approach does not rely on the population installing some apps. They just need to run around with their mobile phones. So when we want to create this heat map of the aggregated location data of infected individuals, we want to use two data sets. So on one hand, we want to use the location data, which is collected from mobile network operators. And on the other hand, we want to use health records from health authorities, which know which individuals in the population are actually infected. However, we cannot trivially combine these two data sets to create our heat map because we are dealing with very privacy sensitive data sets. On one hand, we have location data, and on the other hand, we have health records, so very sensitive data sets. So our goal was to construct a protocol which on one hand produces this heat map that we want to create, and on the other hand protects both of these data sets. So we do not want to give anyone the ability to learn who is actually infected with the disease, and on the other hand, we do not want anyone to give a tool to track the location of any individual. So now let's have a look at how we achieve this privacy-preserving heat map protocol. So when we have a look at the actual process in creating this heat map, we can see that it actually boils down to a matrix vector multiplication. So here on the left side, we have the input of the health authority, which is basically a vector which indicates which people are actually infected. So a 0 here indicates that the person corresponding to ID2 is not infected, and the 1 here indicates that the person corresponding to ID1 is infected with the virus. The matrix, on the other hand, is the input of the mobile network operator. And the elements in the matrix indicate how long each person has been connected to a given cell tower. And when we then perform this matrix vector multiplication, the result is our desired heat map, which indicates how long the aggregated how long all individuals which are infected have aggregatedly spent on a given cell tower. And we now have a look at how we can realize this matrix vector multiplication without leaking these data sets. So our first privacy-enhancing technology that we use is homomorphic encryption. So basically, when the health authority sends its identifiers on who is infected and not to the mobile network operator, it uses a homomorphic encryption scheme to encrypt this input vector to the protocol. So the input is actually encrypted, so the mobile network operator is not able to learn who is infected. But since it is a homomorphic encryption scheme, it is still able to combine this encrypted vector with its location data matrix and produce an encrypted version of the desired heat map. And once it's done, it sends back this heat map to the health authority, who then is the only one who has access to the secret decryption key and is the only one who can actually get the final heat map of the protocol. So homomorphic encryption on one hand protects the patient identifiers, and on the other hand, since the location data is combined with the ciphertext, with this homomorphic ciphertext, the location data is not leaked by the homomorphic encryption scheme itself. However, this protocol has another problem, and that is that once the client has decrypted the heat map still can leak location data. For example, consider when the query consists of only one patient, or we have two patients from completely different regions in a country, then these location profiles of these patients are clearly visible on the final heat map. So in the paper, we propose to protect against this inherent leakage of this heat map by using differential privacy. And this basically works by adding some correctly parameterized noise to the output of the protocol. And this achieves that the heat map is statistically independent to the contribution to an individual. So how does this look in practice? So here on the left side, we have created a heat map for London, where we only included one person, and you can clearly see the location profile of this person on the heat map. On the right side, we then apply differential privacy, and you can clearly also see that the location data is drowned in noise. So the location profile of this individual is not visible on the heat map anymore. But clearly, this also does not give any utility of the heat. Then the image changes when we include a lot of more patients into the heat map protocol. So here on the left side, we have created a heat map for 600 infected people. And on the right side, we also apply differential privacy to this heat map. And what you can clearly see here, that even though individual's location is drowned in the noise, when we have a hotspot here on the left side, this hotspot is also clearly visible on the right side. So the utility of the heat map is still preserved, even though we are using differential privacy. So far, what we have achieved is that the patient's identifiers are protected by homomorphic encryption, and the location data of the mobile network operator is protected by differential privacy. However, the protocol so far assumes that all parties behave honestly. The protocol does not protect against, for example, malicious queries from the health authorities. So if they want to track an individual, what they can do is that when they craft the input vector, which in our protocol is assumed to be 0 or 1, they can set this value of this targeted individual to a much larger value. And what this achieves is that it basically, in the output heat map, it increases the contribution of this single individual. The location data of this individual is then clearly visible on this heat map. And since this is basically a hotspot on its own, differential privacy does not protect against this kind of attack. And also, since we're using homomorphic encryption, the mobile network operator cannot trivially check whether this input vector consists of just zeros and ones. So we had to come up with a different method to protect against this kind of attacks. And what we do is, we have derived some invalidation techniques from zero-knowledge proofs, and they have the goal to invalidate the heat map if we detect malicious behavior. So how does this work? So basically our goal is that we add some value to the heat map, so a mask to this heat map, and if the client query is honest, so if it just contains zeros and ones, then this mask will be 0 and does not affect the heat map. But if it detects malicious behavior, then the mask should be random values and invalidate the heat map. And our mask, our technique, relies on one simple observation. And that basically is that when we subtract each element of the vector by 1 and multiply it to the original vector, then this results in the 0 vector if and only if the initial vector contains only zeros and ones. And in the paper, we show how we can transform this simple observation into this mask here, which provides a high statistical security. So with this technique, we can invalidate the result for malicious queries so that the health authority cannot track the location data of any individuals. So far we have constructed this protocol, and it protects both of these highly sensitive data sets which are involved. So we then, of course, also implemented this protocol, and we used C++ as programming language, and we're using the Microsoft C library for homomorphic encryption. And we benchmarked this protocol for creating a heat map of 8 million subscribers, which is enough, for example, for creating a heat map of the whole country of Austria or larger cities such as Singapore and New York City. And our benchmark showed that creating one of these heat maps just takes 70 minutes. Which is a very feasible runtime in practice. And when we would outsource this computation to Amazon Cloud, this would correspond to just paying $5. So this shows that it's very feasible to create these heat maps maybe once a week in practice. So, but when we want to deploy this in practice, we need to discuss some properties of the protocol. So on one hand, what we have seen in the beginning is that the health authority and the mobile network operator needs to agree on some indices, so to say that ID1 corresponds to this person and so on. So if we wouldn't do that, then the mobile network operator wouldn't be able to construct the correct matrix for that. And in the paper we discussed that we can use existing private set intersection solutions for this agreeing on indices parts, and this adds comparably low runtime and communication overhead to the rest of the protocol. Another thing to consider when we want to deploy this in practice is that people might not want to be part of this computation. So when we have a look at the contact tracing approach, people who don't want to be part of the protocol, they simply do not install the app. So installing the app is basically an opt-in approach to be part of the protocol. For our heatmap protocol, when we also want to give the people the possibility to not be part of the protocol, we can also construct an opt-in solution by, let's say, letting them decide to be part of the protocol when they get a positive test result. For example, if they get it from the doctors, they can say, yes, I want to be part of the protocol, and also when they get an email, they can reply, yes, I want to be part of this protocol as well. And we conjecture that our protocol is still useful, even though when only a small part of the population agrees to be part of the protocol, so that the protocol will produce a nice and useful heat map which helps to track the spread of the disease. So to conclude this presentation, so we have created a protocol which allows to produce a heat map of the aggregated location data of only infected individuals, and this helps in tracking the spread of the disease and helps government officials with taking targeted measures. And we realized these protocols by combining homomorphic encryption, differential privacy, and invalidation techniques that we derived from zero-knowledge proofs. So in our paper we have much more details about this protocol, and this is publicly available on ePrint. And also our implementation is publicly available. It's an open source implementation you can get here on GitHub with this link. So thank you for your attention. If you have any questions regarding our protocol, please do not hesitate to ask during the conference. So thanks again.